Hey class, welcome back. We're taking a look at the second part of multicollinearity and stepwise regression. We're going to focus in on the stepwise regression as the solution for the multicollinearity problem. We'll be looking at pages M14 to M17 today. Before we do that, though, I just want to take a look here at the regression number 1, remember, which was on page M5, and we had that SQF and square footage and fireplaces were significant in that particular model. And they're still significant in regression 4 even when they're together. And so we wouldn't say that there's a problem with multicollinearity. But I'd like to show you what happens if we go back to that first regression where we had all 6 variables and actually take out the 2 significant ones, which were square footage and fireplaces. Now, by the way, this is not something that you would normally be doing here. This is just used to show you here what happens when you take out the 2 significant variables here. So this isn't good practice, but I do want to show you what happens when we do that. So I've taken out the square footage and the fireplaces from the model, and we're left then with 4 variables, which in this case then would be garages, days, rooms, and baths. Now watch what happens when we do that. The R-squared value is 44.4%, and that means that those 4 variables together account for over 40% of the variation in the listing price of the house. Look at the ANOVA test, which takes a look at all of the x variables together, all 4 of the x variables together, and their effect on y. Very high f star value corresponding to a very low p-value, right? Low p-value of 0 indicates high significance because you compare that to alpha. P-value is less than alpha, reject HO. HO is that the variables don't have any relationship together in explaining listing price. And we're going to actually write that all down here. But take a look also at the individual t-tests. And if you look at those, what you find actually is that 3 out of 4 of those variables turn out to be significant at a 5% level. This guy here is marginally significant, but we're comparing that to plus or minus 2, so it's just tucked outside of that plus or minus 2 range, and so it's into the critical region here. So days, rooms, baths are significant when you take out fireplaces and square footage. Turns out garage is also quite important at explaining the listing price of a house, but not when it's in a model where you've got days and rooms and baths, and especially not when you've also got square footage and fireplaces in there. So it's still insignificant, even though a simple linear regression of listing price on garages would show it to be significant. So that's interesting. Let's just complete the F test here. So it says, which of the 4 variables are significant at explaining the listing price of the house? And so in our particular case, then we've got that days, rooms, and baths all have p-values less than 5%. I guess this one here rounds to 5% for days, but it's actually just a little under that, 0.49 something, and it rounds to 5% here. So they're significant. And the only one that isn't is garages with a p-value of 37%. Oops. Show that the 4 variables together significantly explain the listing price of the house. What I'm going to do for this one is I'm going to do the full F test. It's probably a good thing to do just as a reminder of how it works. And so the whole F test, whenever you see this, all 4 variables together, then we're talking about the F test, which is a type of ANOVA test. And so we're going to, oops, Got to see where I place my hand here because it can go kind of goofy on me. So we're saying that the beta for garages is equal to the beta for days is equal to the beta for rooms is equal to the beta for baths is equal to 0 against the alternative that at least one of the betas is not equal to 0. The F star value would be the SSR over P divided by the SSE divided by N minus P minus 1. Now, let's see. Let's take a look at an F distribution. And so this is going to be an F, and its degrees of freedom, remember where you get those, is they're up here. So 4 and 85. 4 and 85. And so your critical region, which is always upper tail F, I'm just going to grab my F table here and take a look at, that's the 1% table. Let me go to the 5% table. So I'm going to look under the 4 column, pardon me, yeah. 4 variables, and go down to 80 degrees of freedom, or 85. I guess the closest is the 60 row, so it's 2.53. So that's the closest that we got by the table. It's going to be a little different if you were to use a function which would look like this: F inverse right tail 0.05 4 85. I'm not going to look that up, but it's going to be something close to that. Anyways, what we get here then is, let's calculate now the F star. And this is just to show you where, again, you get the numbers from. So here's your ANOVA table right here. And we've got, this is a big number. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So 3.37, 1 times 10 to the 10th power. 0.371 times 10 to the 10th power over 4 divided by, and then we've got see, 1, 2, 3, 4, 5, 6, 7, 10. Did I get that right? 10. 4.228 times 10 to the 10th power divided by 85. Yeah, and that comes to, what was that? 16.94, which is way over here. Yeah, so we're going to reject HO. Remember, if you wanted to get the p-value for this, the p-value, which turns out to be basically 0, and you'd get that with an F dot dist. Here, let me do it below there. So that'd be an F dist right tail 16.94 485. And that would give you about 0. So that's significant. So that's just a good reminder of how to do that F test there. Now let's get into how you solve the problem here. Common problem of reducing the problems of multicollinearity is to run something called a stepwise regression. And the best way to do this in Excel is to run something called a backwards elimination stepwise procedure. And so how this works is you start with the full model. That was regression number 1 on page M5, which had all 6 variables in the model. And you run the regression, and then you take a look at the one with the highest p-value, which corresponds, of course, to the lowest, or t-star value, or the one closest to 0. So the one with the highest p-value is the least important variable in explaining listing price of the house when it's in with all the other variables. And so what you do is you eliminate it. You get rid of it. And what that happens then is that you'll find that the R-square may not change at all. If it does, it might go down by a little bit, but you might actually see an increase in the adjusted R-squared because we got rid of a useless variable. And then what we do is we run the regression now with 5 variables instead of the 6 variables. And you do the same procedure. So you continue, you look for the next, the one with the highest p-value, and you toss it. You run it again with 4 variables. You find the one with the highest p-value, you toss it, and you go all the way down until you're left with 1, which will be actually SQF in our case. Determining the best model, right here, depends on the goal of the analyst. If you're simply looking for the best model that will give you the best estimate of the dependent variable, the listing price of the house, then the more variables, the better. So we can add not just the 6 variables in here, but we can add in things like how close the house is to the post office, how close it is to a school, how close it is to a mall, the lot size and things like that, and some sort of measure of the style, and whether it comes with any chattels like dishwashers or things like that, what the capacity of the furnace is. And then you can add stuff like the number of days that the Prime Minister wears a red tie and the birth rate of penguins in the Antarctic. And the point is that you can add whatever variables that you want, and it will never cause the R-squared value to decrease. It will cause the adjusted R-squared to decrease when you've got useless variables in. But the problem is that they'll end up fighting with each other. So if the goal is to come up with the best estimate of the listing price of the house, the more the better. But the problem is that gathering data costs money, there's chances of errors, there's problems sometimes with confidentiality in terms of that and the storage of the data. And you also end up with a model where you can't really tell which are the important variables, because when you got so many, then most of them can become insignificant. So a significant variable can become insignificant. So what statisticians generally do is they use a stepwise procedure to pare it down to what are the most important variables while still maintaining a high R-squared value. And that's actually what we'll do here. So the best model then, which is what we'll consider in this course, is the one where all the remaining variables are significant. And if we were to eliminate any further variables, it would result in a noted decrease in the R-squared value. So let's take a look at that here. I'm going to walk us through a stepwise procedure, and then we'll come back and answer this question here. So on page 194, page M16, we're starting with step number 1, which is the full model, and this is exactly the same as regression number 1 on page M5. So we've seen this output before. And we concentrated before on these guys, which were the important variables, square footage and fireplaces. But in a backwards stepwise procedure here, we're actually looking at which is the most insignificant variable. This guy, rooms. It's got the highest p-value. It's got the t-star, which is closest to 0. And so that's the most insignificant variable. So we're going to eliminate it in the next step. So step number 2 is where we're down from 6 variables to 5 variables. We've eliminated rooms. We'll get a slightly different equation, but what I want you to notice is that the r squared up here in the first regression doesn't even change at 3 decimal places. Still 0.673, 67.3% of the variation in listing prices caused by those variables together. The adjusted r squared changes a little bit. It goes from 0.65, it creeps up a little bit to 0.654. So that's a good thing, actually, because we're getting rid of insignificant variables. All right, let's continue on here. We're going to look at the p-values. And we're going to look for the most insignificant variable. Highest p-value, which is 0.77 for garage. And that, of course, has a really low t-star value, close to 0, 0.29. So we're going to get rid of it. Look at what happens. R squared doesn't even change at 3 decimal places. Adjusted R squared goes up a little bit. Next step, look at the p-values. Get rid of the most insignificant variable, days. Very low t-star value. R squared still doesn't change. It's 0.673 to 3 decimal places. R squared is creeping up. The adjusted R squared is creeping up. All right, let's get rid of the next least important variable, which would be baths. By the way, we never get rid of the intercept. We're only talking about getting rid of the variables themselves. We're not forcing the intercept to be 0 or anything like that. You can't get rid of the intercept unless you force it to be 0, and that's only a special kind of regressions, which we're not considering here. So we're just looking at the p-values for the x variables. Baths is at 0.24%. We're going to eliminate it. We do see a little bit of a decrease here then in the r squared. So it jumps down by about 0.5% here. The adjusted r squared actually decreases just a little bit here. So there's some question as to whether we want to get rid of baths or not. However, getting rid of it only decreases the r squared by a small amount, only 0.5%. And the adjusted r squared almost doesn't change. And baths has a p-value of 0.24. Now remember, when we were looking at the correlation matrix, it was highly correlated with SQF and fireplaces. So there's a multicollinearity problem there. And so we're going to get rid of it and just leave that then with this one here, which was actually exactly the same as regression number 4, where we had square footage and fireplaces in. Now, we could go one more step here and say, let's get rid of the one with the lowest p-value. You'd actually have to take the p-values out to several decimal places. Suppose we could just look at the t-star values, right? So the one closest to 0 would be fireplaces. So we'll get rid of that. And then we are left then with regression number 2, which is just listing price regressed on square footage. So what we've got here is I'm going to back up in terms of the importance of the variables. So we've got square footage, which is the only one left here, is most important, and then followed by fireplaces, followed by baths, followed by days, garages, and then finally rooms. So I'm going to go back right up to the correlation matrix here. That was a ways up. There we go. Oops. So here's the correlation matrix. There we go, right there. Here's the correlation matrix. And remember what we did in the last lesson here was we were looking at the importance of the variables according to their Pearson R's. And so we came up with this list down here. Now, according to the stepwise regression, what we end up with is, let me just flip back here. We end up with square footage still being the most important variable. And then we had fireplaces. And then we had baths. And then we had days, garages, and 6 was rooms. So this is the order of importance. According to the stepwise regression. And what's interesting is, especially what happens to rooms here, notice that it drops in importance from 4th in the correlation matrix. It had a fairly high correlation with listing price, but it drops down actually to being the most useless variable. And that's because of these guys here, because rooms is highly correlated with square footage. And it's highly correlated here with fireplaces and baths in this particular case. And it's got other high correlations as we go through here. So that's a problem with multicollinearity, and we get rid of rooms because it's really not adding anything to it. And we walk through that whole stepwise procedure here. So let's go down here and just fill in that last bit here, which was on page M13 here. So looking at the output from regression number 6, which is the best model for describing the listing price of the house. And so we can just conclude here and then say that we're going to conclude that step 5 is the best. And that's where you had the listing price is some function of the square footage and fireplaces. I'm not going to write out the whole equation. You can do that. Okay. The adjusted R squared was rising as we eliminated variables up to step 4. With the elimination of baths, it slightly decreases. But the R squared hardly changes. When baths is eliminated. So what happened was R squared decreased by about 0.5%. So 0.005. And p-value for baths was equal to 0.24. So therefore, eliminating baths has almost no effect. Eliminating fireplaces and eliminating would cause a big decrease in R squared. So don't do it. So what we end up with then is that step 5 is the best here then, where we've got square footage and fireplaces in. So that's how you do stepwise regression. That takes us to the end here of M17, and the next thing that we'll be looking at is dummy variables, which is the last main subtopic. And so that's where we're going to stop today. Thanks